All right. Hello, everybody. Welcome to this talk about change data streaming patterns in distributed systems. And for this session today, we would like to talk about 3 different patterns which we can use in distributed systems for implementing specific requirements. One would be the Outbox pattern for exchanging data between different microservices. The next one is the Strangler Fig pattern to move from a monolith over to microservices. And lastly, we would like to talk about the Saga pattern for implementing long-running business transactions. And we will implement, or we will show you how to implement those patterns using change data capture, using a project called Debezium, and also how we can use Debezium together with Apache Flink, of course, being at Flink Forward. A few words about myself. I work as a software engineer at Red Hat, and I'm the engineering lead of the Debezium project, which is an open source platform for change data capture. I'm involved with a few other open source efforts. Maybe you've heard about the Quarkus stack for implementing cloud-native microservices. I've been the spec lead for Beam Validation 2.0. And if you would like to know what I'm up to, I would recommend you follow me on Twitter. Now, if I say we, I'm not alone here today. I have the pleasure to be here with my good friend, Hans-Peter Grasel. Hans-Peter.
Hi, my name is Hans-Peter. I'm currently working as a part-time technical trainer at a company called Netconomy, where we are building large e-commerce solutions for our global customer base. Besides that, I'm working as an independent engineer and consultant. I'm mostly concerned with helping them to design and build event streaming architectures, mostly using a combination of Apache Kafka and non-relational data stores such as MongoDB for that. And with that, back to you, Gunnar.
All right, so let's talk about change data capture and what it is about. And really, the idea is pretty simple. It essentially gives you a live feed for the data in your database. So whenever something in your database changes, there's an insert, there's an update, or there's a delete, Debezium will capture this change from the transaction log of the database and will send it out to all kinds of consumers. And the source of those changes, well, as I said, that's the transaction log. So all of the databases, they have this transaction log where they append all the changes, which, for instance, allows us to capture deletes. We will capture all the updates and so on. So Debezium taps into the transaction log, captures the changes, and sends them to consumers. So that's it in a nutshell. And typically, most people use this with Apache Kafka, which allows for a nice decoupling between this event producer, which would be Debezium and our database in this case, and then our event consumers. In terms of consumers, we could have all sorts of downstream systems. So for instance, we could use those change events to sync data into Elasticsearch if you would like to update a search index, or we could use those change events to update a cache, something like InfiniSpan, for instance, or we could just send those events and the data into a data warehouse. So all those kinds of replication use cases. And really, this is based on Apache Kafka Connect, which is another effort from the Kafka ecosystem, and it's a runtime and a framework for building and then running those connectors. So it's you do those data pipelines by means of configuration. It's typically no bespoke programming involved. So that's replication in the widest sense. But then you also can, for instance, use this to implement streaming queries, as we will see with Apache Flink, or you can use it to exchange data between your microservices, which we will also touch on. And now really Debezium, well, it gives you this log-based change data capture, by the way, which is in contrast to a polling-based approach where you would go to your database and you would poll in, every second or every 10 seconds for changes. So this is log-based CDC. And really it's a full platform and full CDC platform. So this means it gives you all kinds of features, for instance, like initial snapshotting. So typically, if you set up a connector, you won't have the transaction logs from last year or something like that. So this means we will have this notion of an initial snapshot to get a current state of our data before we then start to stream the changes from the log. There's things like support for this Outbox pattern, which we will talk about in a bit. And also there's a UI and all kinds of things. So really, it's a complete open source CDC platform. So it's Apache licensed, so everybody is invited to use it as to please, and of course also to contribute. So we have a very active community and very active open source community around Debezium with all kinds of people from different companies contributing. And lastly, there's really very impressive large deployments in production. So we see users which have hundreds or thousands of databases, which they then monitor with Debezium to extract changes and send them towards any sorts of downstream consumers. In terms of the connectors, well, there's no one single API which would allow us to get changes out of the transaction log from any sort of database which means we need to have a dedicated connector for a database which we would like to support. Currently, we have support for the ones you see here. So we have support for Postgres, MySQL, MongoDB, SQL Server, and quite a few others. There's a group of stable connectors. So there we are really very conservative when it comes to changes to the event format. You really can rely on this format being stable. And then we have 2 more connectors for Vitesse and Cassandra, which are NoSQL databases, which are currently in the incubating state. So they are under active development. The event format might change, the configuration options might change, and so on. Now, I mentioned most of the times people use Debezium with Apache Kafka and Kafka Connect. I would guess maybe 90% of Debezium users are using Debezium that way. But then you also have alternatives for deploying Debezium. And this is actually very interesting when we think about Apache Flink. So the first option, or let's say the second option, besides the Kafka Connect-based deployment, that would be using the Debezium embedded engine. So in that mode, you use Debezium as a library in your Java-based application, or I should say your JVM-based application. And you just essentially, you configure the connector programmatically. So in this case, it's a programmatic usage. You point essentially it to a callback method, which it should invoke whenever there's a change event. And then you can use this embedded engine for integrating Debezium in all sorts of use cases. So you could send those events, for instance, to a browser using WebSockets, or you could use it to integrate this with Flink, as we will see in a bit. So that's the embedded engine. And then there's another effort. This is called Debezium Server, and this is what we see on the visual here. And Debezium Server is essentially its own ready-made runtime, which is based on the Debezium embedded engine, and which then lets you take those change events and send them to other messaging infrastructure like Amazon Kinesis, Google Cloud PubSub, Apache Pulsar, Redis Streams, and quite a few others. So if you're not in the Kafka universe, you can still use Debezium and you can benefit from its CDC capabilities using Debezium Server via all those messaging infrastructures you see. Now, when I say change events or data change events, we also should talk just briefly about what this means. What is the structure of a change event like? And this is what we see here. And essentially, there's 3 big parts of which are within each change event. So first of all, there's what we call the before and the after part. So they describe the actual record or a document in case of MongoDB, which has changed. And you will see this previous state of a row, and you will see this new state of a row. So within before and after. Within those 2 blocks, well, you will have a structure which resembles the table you're capturing. So for each column in your table, in your relational database, there would be a field within those before and after blocks. Now, if this is an insert event, well, we would have it before, right? Because a newly created record, it just has a new after state. So that's before and after. We see those here. And then there's some more metadata, which is part of the events. And this, for instance, describes what's the version of the connector, the name of the database, maybe the schema, maybe the query, which triggered a specific change, timestamps, positions, position in the log file, all this sort of metadata, which allows you to uniquely identify the origin and the identity of a change event. And lastly, there's those 2 other fields, up, which describes what is the kind of change. So it could be an insert, an update, or delete, or a snapshot event. And there's a timestamp, which tells us when Debezium processed this event. All right, so this is Debezium in a nutshell. Now let's go over to Hans-Peter and let's see how we can use this idea of CDC for propagating data changes between microservices using the Outbox pattern.
Okay, so let's start by discussing the Outbox pattern. So the Outbox pattern helps us to solve a fundamental challenge that we face when we are talking about distributed architectures or several microservices that would need to exchange data. So let's say very often we have not only the case that a microservice needs to update its own local database, but in addition, it wants to notify other collaborating services about some of the changes it made. And of course, we want to do both these things in a consistent way. Now, one pretty naive and actually inherently unsafe way to do that is what we would call a dual write. Now, we talk about dual writes anytime an application tries to update 2 resources that are not capable to share one and the same transactional scope. For instance, in this example here, we see a microservice that tries to update its own local database. And in addition, it wants to communicate some events by producing a message to an Apache Kafka topic. Now, again, we are not talking about a distributed transaction that we could span across these two different kinds of storage systems. So this is, of course, prone to errors. And it's only a matter of time until we see inconsistent data or corrupted state. Now, the Outbox pattern allows us to solve this problem. And the way this actually works is that the Outbox pattern allows us to communicate to a separate system in a safe way. So here we see our order service that writes to a local database, and it updates its two business tables. We have here the orders and order lines table, and it does that as usual. But in addition to that, and in the same transactional scope, it also writes to a separate table, which we call the Outbox table here. And this Outbox table will be used to store whatever we want to communicate to a different service. Now, we would then set up a data processing pipeline using Debezium, in this case, a source connector, let's say for MySQL, that will listen to the changes, but it will only be interested in the changes that are made to this Outbox table. So it will ignore the actual changes that are made to the orders and order lines tables respectively. When it comes to the structure of how this Outbox table would look like, we are basically free to design that in a way that we would need it for our own purposes. So in this example here, what we see is an Outbox table that is borrowing the ideas from an aggregate structure, which we know from domain-driven design. Now, when we do it that way, it can well happen that sometimes we have the case that this Outbox table event contains an identifier which refers to some data in an external system. And this would then mean maybe we want to refer or resolve additional data based on this ID in flight. And we can also do that by using a modified version of this Outbox pattern and additionally bring in some stream processing technology into a place such as Apache Flink. And the way this would then work is that Apache Flink, we would write a stream processing job with it. It would listen to this topic that stores the original raw Outbox events as they are sent by Debezium. And then it could, based on an ID that is contained in the payload, ask as an external system, basically looking up additional information to the original Outbox table event, enrich this raw data, and then write this data back to another Kafka topic for downstream consumption. So this is all what we wanted to share for the Outbox pattern for now. But let's ask ourselves how this integration between this Debezium change events and Apache Flink could look like. And basically, we have two options here. The most commonly found option is, I think, still the way that Debezium is used within a Kafka Connect context, so that Debezium then writes those change events into the Kafka topics, exactly as we have seen that on the illustration of the previous slide. And then we would create a Flink table based on the Kafka as a source topic. So Flink would read from the Kafka topic directly and process these change events accordingly. A second option would be to use Flink CDC connectors. And Gunnar mentioned that earlier. So here, the Debezium embedded engine can be leveraged so that Flink basically can use this engine to directly talk to the database using the embedded engine of Debezium and read in those change events from there. So in this particular configuration, there would be no need to operate a Kafka Connect cluster in addition to that, which would run the actual Debezium connectors for us. So for now, that's all we wanted to share about the Outbox pattern. And let's discuss the second pattern, which is the Strangler Fig pattern. So the nice thing about that pattern is that we can describe it based on a pretty memorable analogy we find in nature. So what we see in the background of this slide is a huge tree structure, and the tree itself is wrapped in some other species of plant, and they are called strangler figs. Now, the special thing about those plants is their growing behavior. They seed in the upper parts of their host trees, and then they grow downward until they root in the soil themselves. And over many, many years, they are capable to fully envelope the original tree, and which basically means that they will eventually and slowly kill their host. Now, I'm telling you this because we can transfer this analogy into a technical context, and we can learn how the strangler fig behavior can also help us with a real-world problem, namely that of a system migration. I think many of you know, or at least can imagine, that there are several challenges involved when we try to migrate existing systems into newer forms. Let's say we want to get rid of an old monolithic application and want to replace it with a modern microservices architecture. And then it's very rarely a good idea to try such a migration, given a reasonably large and complex system, in one big bang. So ideally, we find a different way so that we can gradually and slowly evolve from an old monolithic application towards a microservices architecture. We do that because big bang migrations are oftentimes doomed to failures, and of course, we want to avoid that. But how can this actually work? And for that, let's take a closer look at a fictional example we brought here. It's a legacy monolithic application which provides functionality for a pet clinic. And this application was written with an old stack. It still runs on Java 6 and Spring Framework 3. So we just pretend here it was never updated since it was developed originally. And now we want to set out to try to migrate such a system towards a microservices architecture. So in a first step, what we would do is we would introduce some kind of proxying mechanism. And this proxy for now will route all requests or reads and writes still to the monolithic application. Then we would think about, well, if we want to extract one particular component, let's say we start with the leftmost one, with the owner's component, extract it into its own microservice, then of course this microservice will need to be backed by its own data store and will need the corresponding data that is stored for the owners in the monolith. So here we could, in a first step, try to define a change data capture pipeline using Debezium and Kafka running in Kafka Connect to bring all the existing data that is related to owners over into separate Kafka topics. And from there, we could then configure a second connector, a sync connector, which in this example would feed this data into a MongoDB collections. So this MongoDB database then is there to back our microservice that we want to develop next. So back on the application layer, we can then start the actual migration, extract this owner component related functionality from the monolith, put it into its own microservice. And here we are, for instance, using Java and the Quarkus framework to do that. We can do this migration or extraction in multiple steps too. So first we can say we only want to support read-based scenarios, which basically means that once we have done that and the service can serve those reads, we can reconfigure our proxy such that all the owner-related reads are then served by our new microservices. The writes would still go back, and also all the other requests would still go to the monolith, of course. Then, if we want to extend the scope of the microservice, we can say, well, let's implement the write scenarios. And once we have done that, we can also instruct the proxy by means of reconfiguration to redirect those writes to the microservice as well. At that point, it's very important to mention that we should only ever have one source of truth when it comes to writing. So as soon as we do that, no writes related to owner-related data should happen on the monolith side. Also, we want to update the existing change data capture pipeline and instruct the Debezium source connector not to track any changes of the monolith's database regarding owner data any longer. Another thing that's important is that the other components in the monolith might still rely, of course, on changes that are now separately handled in the microservice and its own database. So we would need to find a way to synchronize these changes back. And again, what we would do is we would configure another change data capture pipeline in the opposite direction. Then we have migrated one of those components, and we would then repeat this whole procedure until we eventually have migrated all of the components, and we could then at one point safely shut down the monolith. Now, when you are interested to try this out, you can go to this link here from the page. It brings you to a GitHub repository where we have a fully working example of exactly this case that we are discussed here on the slides for you. When we take a second closer look and try to summarize the benefits here that this Strangler Fig's behavior and pattern gives us, we can say that we can reach our ultimate goal of migrating a large complex system by just taking baby steps. We do it one by one, component by component, or module by module. Also, another important thing is that we have to do it, of course, in a way that both old and new can coexist. This means at any point in time, we could pause, or maybe we decide to even stop our migration efforts and want to live with a hybrid scenario where parts of the workload are served by microservices and parts are still served by the monolith. That's also a viable solution. Ideally, when we do it in a proper way, we could even implement this so that we can have a safe path to roll back anything that we extracted. Maybe we realize afterwards one extraction into its own service wasn't a good idea, then we can roll it back. Again, the bottom line here is that we want to minimize the migration risk and avoid a big bang. When we look closer to the CDC pipeline of such a solution, we might come up with some challenging questions. Now, first question, of course, is related to the data model. If we just do this puristic form of CDC, where we essentially move data on a record by record fashion, one by one, aren't we leaking the data model from our monolith? Another question is, instead of this one-to-one record by record replication, can we find a way that we can build aggregates in flight? Maybe in our case, we have a target data store that stores documents, MongoDB, so it would be a pretty good fit to do something like that. And yes, these are legitimate concerns, but the good news is we can address them by enhancing our CDC pipeline. So first, we could just introduce single message transforms at either side of our data flow. And these single message transforms, they allow us to manipulate the change data capture payload from Debezium in flight. So we can do things like rename fields or only include or exclude a subset of the payload's fields. We could do data type casts, date time harmonizations, things, and many other things as well. Where these SMTs cannot help us is with building aggregate structures, or in general with acting upon more than just a single record. So for that, we would use a stream processing technology. And again, here, Apache Flink comes into the play. We can write a Flink job. And this Flink job could, for instance, do something that is very common in such an architecture. Namely, it can help us to join parent-child relationships as they are commonly found in relational database systems in flight. So again, we can do that to build an aggregate structure while the data moves from the monolith into Kafka topics and from there then into our target data store. Here is a concrete example to understand that a little bit better. And again, it refers to the same application that we discussed earlier. So what we see here is two tables of the monolith's application. It's the owners table and the pets table. And this is this typical parent-child relationship. And of course, a change data capture pipeline based on Debezium would now write these change events into two separate Kafka topics as well. And now we want to introduce a Flink job, which allows us then to, first of all, join those records together. And in a second step, we want to group those records that refer to the same owner ID, which is in this case the foreign key relationship between owners and pets, and then come up with a custom aggregate as a result. So we see that on the right in a JSON serialization. It's just then a document, if you want, that contains owners and the pets they own in just one consistent piece of data. And this data can then be used as by a sync connector and be written into a MongoDB collection, for example. So the way this would work in Flink, two options, broadly speaking. We could use the table API for that. In this case, I have shown all those tables in separate steps so that it's easier to see what's going on. So the upper two tables are just Flink tables that represent the change events that Debezium writes into, for instance, a Kafka topic. Then we use the table API to run this join operation. So this is the third table in this snippet. Owners joined with the pets. And then the fourth table is what results from grouping and aggregating this joint data together so that we end up with this aggregate that we have just seen on the previous slide. Another option is that we use Flink SQL. So we can write the same thing with just basically a single SQL query as we see it here. The only thing that's missing here is defining those three user-defined functions that I prefixed here with ff21 underscore so that we see where some custom code would come into play for this aggregation of the joint result here. With that, I want to hand over to Gunnar to tell us more about the third and final example pattern of this talk, which is all about sagas. Back to you, Gunnar.
All right. Thank you so much, Hans-Peter. So then let's come to the third and final pattern of this talk, which would be the Saga pattern. Now, let's assume we have moved from a monolith over to microservices, maybe using this Strangler Fig pattern, which we have seen before. And now we are in the situation where we have a deployment of multiple microservices. And of course, we aspire for those services to be as independent as we possibly can. So really, they shouldn't share databases. They shouldn't share state. They should be self-dependent as much as we can. But still, the truth is, as much as we try, very likely we will have a situation where multiple services need to act in coordination. So they need to work together and they need to collaborate to achieve a consistent outcome of some sort of long-running business transaction. So very likely this will happen. Let's say we come back to this order scenario where we would like, for instance, to have an order service or a customer service to collaborate. Now, the challenge there is we really cannot do this using things like distributed transactions or two-phase commit protocols. The reason being, well, first of all, they are typically not exposed at the level of microservice APIs, so we just cannot use them. But then even if we could, we probably wouldn't want to do that because, well, those distributed transactions, they will limit us in terms of the availability of the entire system. So if one of the services isn't available, well, our transaction would be stalled and we would have some sort of problem. And of course, we also need to achieve consistency in the face of failures. So let's say one of the services cannot proceed with its own local part of this overarching business transaction. We will want to have one consistent final outcome still at the end. So that's the challenge which we have. And now let's see how Sagas can help us with that. And the idea essentially really is to break down such a long-running business transaction into multiple local transactions, which then run within each of the contributing and participating services. So here, let's say we have such an order placement flow, and we have those three systems: order, customer, and payment. And now the flow is like this. An order gets received, and there, well, we want to do some sort of credit limit check. So we would like to know whether this customer still is allowed to place another order, or maybe they have too many open orders already, and we don't want to accept this further order. So let's say this credit limit check, and this happens in the customer service, this succeeds. Then we would move forward with the flow over to the payment service. So we would like to request the payment for this. And provided this payment also comes through, then this order would be in some sort of accepted state, and it would be ready to be fulfilled. So that's the happy path. But then, of course, we also could have failure situations. So let's say this credit limit check fails. Well, then it's easy. We would just go back to the order system and we would have, an order rejected state. But things get more interesting if this credit limit check step already succeeded. So now we are on the payment step and that one fails. So now at this point in time, we need to do what's called a compensating transaction in this customer service, which essentially undoes what has happened in the customer service before. So it reverts what it did before by using this sort of compensating logic. And again, we would be back at the consistent end state in the end of the day. What we also see here is that our transaction guarantees, they are reduced when we compare it to classical transaction semantics. In particular, the isolation aspect, that's limited. So our local transactions, this credit limit check in the customer system, this already got exposed to other users while this entire flow is still running. So the isolation property, that's not given as it would be given with usual transactions. So how could we implement this using CDC and Debezium and those kinds of things? Well, of course, we could think about some sort of HTTP-based approach, but then again, we would be back to this close coupling. So what do we do if one of the systems isn't available? How do we handle the situation? Would we have to buffer all kinds of requests until those other systems are available again? And well, the Outbox pattern, which we have seen before, it provides an answer to us to solve this problem. So the idea is we would use the Outbox pattern in each of those services for implementing those messaging flow. So if our order system receives the order placement request, it would persist the order in its local database, and then it would send a message to this customer service using its own local outbox. So there would be no direct, no synchronous coupling between order and customer. Customer would do the same. So it would do the credit limit check and it would send back a reply message back to the order system. And again, the flow would continue to the payment system. We would request a payment and it would either succeed or it would fail. And then the order system would be in its final state, or it may have to do this compensating transaction with the customer system. And all this nicely decoupled using change state capture and the Outbox pattern. So let's look at it from a perspective of this sort of execution flow here. And what we see there is this compensating transaction situation. So first of all, the order system does this credit limit approval request with the customer system. This succeeds. So now we know we can go to the payment system, request a payment. And now let's assume this payment fails. So this is where this compensating transaction comes into the picture. So now we need to release essentially this previously allocated credit amount. And the customer system, the flow would return to the order system, and we would be in a final state. So how would this look like in terms of an actual implementation? And I'm going to show you just a few key parts here of this. And the first one would be the Debezium connector, or let's say one of the Debezium connectors, because we would have one for each of those three systems. And in this case, it's the configuration for the connector, which captures the changes from the order system's Outbox table. So we see here, you configure it with the credentials of the database, host name, and so on. Where can we find the database? Then we have this filter configuration. So there we specify we are only interested in the changes of this Outbox table, so the Outbox event table. We are not interested in any other changes. In particular, you're not interested in the changes to the actual core business tables. And then there's this transformation here, which uses this Outbox event router component, which comes with Debezium. And essentially, this just helps us to propagate this message format, which we would have written into this Outbox table, and propagate it as a nicely formatted message into an Outbox topic. And also, it would route, for instance, the event into different topics based on the aggregate type. So it comes back to this notion of domain-driven design. There would be a column which describes the type of a specific aggregate, which is represented by an Outbox event. And then this event router would send this message to the right topic based on this aggregate type. So now we could take a look at the actual messages as they flow between the systems, but that's not so interesting. What's more interesting is to see what is the execution flow of this system, of the entire Saga execution. And for that, we need essentially to have what's called a Saga execution log. So this keeps track of the state of a Saga instance. And also, well, there needs to be a component which controls the Saga flow, so like a Saga orchestrator. And here in this case, this is all implemented in this order service. By the way, we will have the link to the example at the end of the slides. So here, this is all implemented in this order service. And now the Saga execution log in this order service, it's just another table. And here, what I did here is I just captured the changes from the Saga execution log table, so to see what's going on. So for each of the state transitions, we see a message here in a Kafka topic, just for the purposes of examination. And there's a few properties which are in particular interesting. There's this current step property. So this tells us at which step of the flow we are. So current at the beginning, we are there's no step, so it's the initial one. And then later on, we are on the credit approval step. And we also see how those status attributes change accordingly. So first of all, we are on the started state, and there's no status for the specific or for the individual steps yet. And then in the second event, we see, okay, now this Saga has started, and this credit approval step has started. So that's what we see in the step status. And then if we could continue, and now here we would see, okay, once the credit approval message came back, or the reply message came back, our credit approval check is in the approved status, and now this payment step is in the started status. And lastly, in the final message, we see, okay, the entire Saga flow has completed, and also the individual steps have completed. And of course, we also could take a look at another example where we would see this compensating transaction, but the principle would be the same. So that's how we can use CDC to implement such a Saga-based coordination flow in a safe way. And again, the question is, of course, how could we leverage Flink in this context here? And well, so let's say we implement a Saga not based on the Outbox pattern. So maybe we are fine with implementing it based on changes on the actual business tables themselves. So we don't always have to use something like Outbox, right? It could also be a valid choice to capture changes from the business tables themselves. So let's say we do that. We capture changes, for instance, directly from the customers table in the customer system. And now there's, depending on the specific database which we use, it might happen that we receive what's called a partial change event. So here in this case, this is coming from Postgres and Debezium's Postgres connector. We see here in this biography attribute, there's this placeholder, Debezium unavailable value. And this happens for specific columns in Postgres, which are called toast columns. Essentially, their value isn't stored in the transaction log. And now what happens is if there's a change to such a table, but then this particular toast column hasn't changed, we will not receive the value, the unchanged value from the Postgres database. So this event is not fully self-contained. So we get the values for the other changes, but we wouldn't get the change, the unchanged value for the biography column. So that's what could happen for an update event in case of Postgres. And now the question is, how can we materialize full events still? So maybe our consumers, our order service, it would actually rather have a complete event, also those unchanged toast columns. And now this is where we could leverage Apache Flink again, because we could use it to enrich our incoming partial events with the full state, which persists in the state store. So the idea would be if we receive the insert event, and this always has the full state for all the columns, we would persist that information, or maybe just the information from that particular column, in a state store in Flink, so for instance, based on RocksDB. And then if we receive an update event, which contains this placeholder value, then we will know, okay, we need to go to the state store, fetch the value for the biography column, and write it into the change event, and then send out this enriched change event to the other consumers. And then that way, the consumers, they would be decoupled from the fact or from this notion of partial change events. Of course, the price which we pay, well, there's some sort of increased complexity. And also, of course, the state store, well, it doesn't come for free, right? So we will have to store that information, but then things just get easier for our consumers. All right, so this pretty much concludes what we wanted to talk about today. And just to give you some wrap-up or some key takeaways, well, I hope we could make the case that change data capture and Debezium as one particular open source implementation of this pattern is really a very powerful tool in your box. So if you implement event-driven architectures with microservices, distributed systems, CDC can help you to implement things like exchanging data between different services, moving over to microservices or implementing those long-running transactions. So it's a very capable tool, and you should consider it for implementing those sorts of requirements. Debezium, as I mentioned, it's an open source CDC platform. So it comes with connectors for all kinds of databases, as we've seen. It comes with support for things like the Outbox Pattern, much more. So it's a ready-to-use toolbox for implementing change data capture flows. And lastly, I hope we also could make the case that combining Debezium and Apache Flink takes it even to the next level. So it gives you a very powerful combination of those two tools, and you can use it then for doing things like enriching your events, like expanding those partial events, for joining topics, and quite a few other interesting use cases. So definitely Debezium and Apache Flink, it's a very interesting combination of tools to be used together. Lastly, a few resources. So if you would like to learn more about the Outbox pattern, you can find this write-up on the Debezium blog. The Strangler Fig Pattern, the term was originally coined by Martin Fowler, so you can read more on his blog. I wrote a post on InfoQ about the Saga implementation using CDC. And lastly, we have this Debezium examples repo where we show all kinds of examples of the Outbox patterns, Saga patterns, those toast column expansions, and all sorts of other Debezium and CDC usages. That's pretty much what we had for you today. We would be very happy to answer your questions. And thank you so much for attending, and see you soon.